Recordings rolling. It is Tuesday, April 1st. So yesterday we did most of the review for oscillating motion. There were a couple things right at the end I wanted to get. So we're gonna have you guys draw some graphs. Okay, so you guys got some paper out for some graphs. We're gonna do some graphs together. Okay? And then we'll go into fluids. Okay, so that's unit 8. Here's my mnemonic device for fluids. I think ABCP. That's Archimedes, Bernoulli, conservation of fluid, Pascal. That covers most of the topics that I want to do, but we'll do a review on that. Right, so you guys remember for a few days now, AP Practice Exam 2 multiple choice questions have been open. So those are due by the time you guys come to school next week. I might bump this due date a couple of days because I don't think we're going to get to go over the solutions by Monday, but probably a good idea to have most of this done by the end of the weekend. And then FRQs. So this is my plan is the next 2 days, I'll give you guys FRQs. I have them all printed, ready to go, got the new packets. So I think you guys said you wanted to work in teams. I think that's a good idea for this one. And the third practice exam, I'll have you guys do alone. Okay? And we'll do a trade score just like we did for the first exam, starting on Friday. That'll, of course, probably take us a few days to go through the solutions. Right. So any questions about agenda? Anything going on? What's wrong? All right, so let's go back and finish this simple harmonic motion and oscillation. And so we're looking a lot at this yesterday. So there's two main scenarios that cover most of oscillation. Right, you got pendulums and blocks on springs. Okay? And so I remember this. We're looking at proportional relationships and what is a variable, what isn't a variable. Right? So guys, what if you increase the mass of this bob right here? What happens to the time period? Yeah, stays the same because mass is not part of this equation. Right? You guys said, right? Same thing with this angle. If you change from 5 to 10 degrees, this doesn't change either. Right? But the gravity field matters and the length of the pendulum, that matters too. Right? I probably mentioned the string as thing. So if you have let's go 9 times the length of the string, that'll be 3 times the time period and so on. Right? There's some linearization graph, blah, blah. Right? Actually, most of these I put away. Right? Here's the block on the spring version. It looks really, really similar. You guys did a whole lot with this. I gave you guys some spring. You guys remember handing those vertical springs from the ring stands? Okay, and then you pull the block down, let it go. It goes wow, 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 oscillates. Okay. Actually, that's what I'm about to have you guys graph. Yeah, you guys had a big old lab table, look something about like this. Okay, so if you were asking experimental design, you might say, oh, okay, I'll hang a spring vertical from a ring stand. I'll hang one of these lab masses from it, and then pull it down a centimeter and let it oscillate and time this with a timer, maybe for 10 oscillations, and get all information out of that. Here's some common graphs. You guys know AP loves linearization. We've done a ton of linearization, and we did some examples yesterday too. So like what's going to linearize, did a bunch of those. But what I want to do is make graphs that look more like this last one here, just to wrap up this review. Okay. All right. So we're going to put basically these graphs together. Okay? And I'm going to have you guys, or give you guys some numbers. We're going to do some calculations, whatnot. Okay? But what's going to lead into making these graphs is you have to know this page right here. Okay? So you guys know time period and frequency are reciprocals of each other. Okay? So here, let's say I have this mass on a spring, and I pull it down and I let it go. It goes wow, 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 wow. It takes some amount of time to oscillate. Guys, what is the time for oscillation? Is it from the top to the bottom? Or is it the top to the bottom, back to the top again?
Top to the bottom.
Yeah, that full the second thing I said, the top to the bottom, back to the top again. It's one full oscillation, and however much time that is. Now, suppose that was 2 seconds. It was like, wong, 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 wong. You guys see it takes about 2 seconds to cycle? Okay. Let me get this phone call. Pause this. All right, and we're back. We're back. Right, so guys, if the time to oscillate was 2 seconds, what would the frequency be? Yeah, 0.5 hertz, right? And okay, that's very good. All right, so frequency is how many cycles per second, and that's hertz, so like 1 over seconds. All right. Also, you guys see this angular frequency down here? Now, this omega we normally in this class use for angular velocity, but that's not what it means in this context. Okay? It's just a consolidate. It's a different type of frequency. It's called angular frequency. It's going to help construct the graphs. And so just take the regular frequency, like 0.5 hertz, for example, okay, and multiply by 2 pi, and that will make these graphs a lot easier to craft the equations for. Okay? So what about here? We've got amplitude times cosine of, ooh, look at that. Look, it's that 2 pi times the regular frequency. In fact, if you want to write up the whole thing, that's okay too. Okay, that's what feeds in that. Okay. Now, normally start with a cosine because at time zero, there is an initial displacement, which would make sense if it's not already in motion. Okay, you have to maybe pull this down a centimeter or pull this one angle from the vertical to set it into motion. Right. So that's why you normally start X versus T with the cosine, although you don't have to, but makes sense. Okay. And then the rate change of cosine turns out to be negative sign, which has something to do with velocity in this case, right? Because rate change of position is velocity. And then the rate change of velocity is acceleration. Rate change of sign is cosine. And if the negative was already there, it's still there. Okay. The amplitude stays out there, but you also have to extract out this angular frequency, which is why it's nice to consolidate it with that omega angular frequency there. Okay. Right. If you're in calculus, you guys know it's called the chain rule, right? See that omega coming out and then coming out again. Okay. So let's do a numerical example. You guys ready for this? Okay. Right, so you guys got some notes. Let's do here's scenario. Okay. Let's do a block on a spring. I'll give you the mass of the block equals what's this one right here? This is 200 or no, this is 100 grams. 100 grams. Let's just use that. So 0.10 kilograms, wouldn't it be? Isn't that 100 grams is 0.1 kilograms? Okay. And let's say that the time to oscillate back and forth, I'll call it capital T for time period. Let's have that be 2 seconds. Okay, 2.0 seconds. Okay. So some things I want to know. What is K equal to? How stiff is that spring? What is K? Okay. And then we're going to make a bunch of graphs. So I'll set up some axes for some graphs. While you guys are setting up some axes and also solving for K. I want to do all those things. We got what's the vertical displacement of the mass as a function of time taken along? What's the velocity of the mass as a function of time? What's the acceleration of the mass as a function of time? Okay. Okay. Notice I only gave you two numbers. I gave you the mass of the block and the time interval. Okay. All right, so I'm going to solve for the spring constant, K, and you guys do that too. Let's see, what is the spring constant? I got the spring constant. Who else got the spring constant? What you got? All right. Yeah, Alex got it. All right, who else got the spring constant? Who knows the spring constant? Okay. Actually, can't quite make the graphs yet. I didn't tell you how much you pull it down. Okay. Who else has the spring constant? The spring constant. All right, let's go over this then. So, guys, to get the spring constant, what formula do you use? Yeah, time period equals 2 pi times the square root of m over k. Okay, which on your equations is right here. You see right here, about 2/3 of the way down, right here. Right, so time period for block on a spring, boom, right there. Okay. Now you guys know, you guys have seen lots of these that AP likes to give you a whole table of data where they put in different masses. I had you guys also do it on your lab. So like you change out the mass and you like linearize the whole graph, right? Well, we'll do even simpler than that. We're just going to plug in one set of values. So I know for if it takes 2 seconds, so where the time period goes, I'll put 2 seconds. That'd be 2 pi times the square root of, and where the mass goes, I got 0.1 kilograms. 0.100 kilograms. So that's 100 grams, but it's in terms of kilograms, based on that unit. Now I can solve for K. Right, isn't that instead up there? Okay. Oh, yeah, what could have been good too? Could you guys have solved this in terms of variables? Yeah, so you could have left the variables there. Actually, should I do that too? Maybe split the page. I used to do this with you guys too. Right, so what if I solve it in terms of variables over here, solve it numerically over here? Right, so I can divide down to 2 pi. So 2 seconds divided by 2 pi equals the square root. Okay, and then in terms of variables, it would look like this. T over 2 pi equals the square root. Okay. Next step, I can square both sides. We got to take care of that over here. So 2 seconds over 2 pi, and then square that. So over here it's 0.1013 equals 0.100 kg over k. Or in terms of variables, it'd be like t squared over 2 pi quantity squared equals, that'd be m over k. Okay. And so you can cross multiply this k and divide down all this crazy stuff on the left side. I'm getting k equals, so it's 0.1 kilograms divided by all this stuff. Yeah, 0.987, and that's newtons per meter. Oh, I should have asked you guys the unit. You guys would have said spring constant is in Newton per meter, right? It's how stiff springs. Right. And in terms of variables, I do k equals 2 pi quantity squared divided by t squared. This is all times m. Okay. Right. So there it is. So you could get any answer. Right. And so you guys good with that? Yeah. Right. So now I know how stiff the spring is. Now to make these graphs, I still have to tell you how much I pulled this down. So let's say I pull this down. I'll say A for amplitude equals about 0.01 meters, which is like a centimeter. Isn't that 1 centimeter right there? Just pull it down about that far. It goes one, right, about like that.
No, this is just for
Oh, okay. Yeah.
testing episode.
Oh, okay.
That's for me.
Oh, okay. Yeah, okay, go ahead. All right. So, so you guys ready to put these graphs together? Let's figure out let's get this angular frequency could be helpful because I told you the time period is 2 seconds. So let's get the frequency. So if time period is 2 seconds, then when the frequency be 1 over 2 seconds, which is like 0.5 hertz. Right? And then the angular frequency, which is 2 pi f. Right? That'd be, well, oh, look at that. Actually, 2 times 0.5 is wash. So pi. So wouldn't that have to be 3.14? And now the unit still hertz. So it's just a different type of frequency though. That's helpful for making the graphs. Okay. So we got the regular frequency and here's the angular frequency version of the same thing. Right, now what? Right, so here's our model. Let's start with position versus time. So position as a function of time, if you like, equals amplitude times, I'll do a cosine, and then I got the angular frequency times time, just like that. Okay. So I told you the amplitude was like a centimeter, and in terms of meters, that'd be 0.01 meters. I got cosine as my function, and omega, that's this number right here, point. So 3.14 hertz if you have a unit in there. And then t is a variable because time's just ticking along, so that's my independent variable. And here's how far it's displaced as a function of time. Right? Right, so that'll be like that. Okay. All right, so what does that look like on the set of axes? Like, how much time would it take to cycle? Well, I know the answer to that. It's going to be 2 seconds to cycle, right? 2 seconds. So I'll go over to 2 seconds. So it's be time in seconds. I should label my units. These are all seconds. Okay. Got something at 4, something at 6, and so on. 2, 4, 6, 2, 4, 6. And then X max I know is okay in meters, it's like 0.01. So I'll go up to there, right? Now, you guys know every 2 seconds it's going to completely cycle, isn't that right? Okay. So here, go ahead. You guys draw the rest of that graph. I'm really helping you guys out by throwing some numbers on the axes. Go ahead and draw the rest of that graph. You know, every 2 seconds it completely cycles. Let's say it starts at the point that you're letting it go. So it starts at the amplitude. See what these graphs look like. Are you guys able to make these graphs? Okay, so it's going to be a cosine graph, right? Yeah. Okay, it looks about like that. Yeah. Okay. All right. I think Evan got a cosine graph. Oh, Hans has a good looking graph. Hector has a good looking graph. Alex got it. Landon got it. All right. There you go. So at time 0, I'm just releasing it. Okay. And it doesn't get back to that point until after 2 seconds. Okay. In the meantime, it's done this whole thing like that. Okay. And then if there's no frictional losses, then it'll just keep doing that forever. Okay, so there's another cycle. There's a third cycle. Right, that's 3 cycles right there. Oh, God. Right. Now, that should, guys, this graph should be described by this equation. Let's see if that's true. See if it's true. Now, I'm going to flip this calculator from degrees into radians. You guys see how I have cosine of something? Okay, so let's put this in radians for sure, right? Okay, and let's see. So according to this, guys, what time is this right here where it zeroes out? What time is that? 1.5 seconds. You guys see this 1.5 seconds right here? Because this is 1 second. Wouldn't this be 1.5? Right. If I plug in 1.5 seconds right here, this should all be equal to 0. You guys think that's true? Let's see if it is. So 0.01 cosine. Well, I know what 3.14 is. So I'll just use pi. That's really what that came from. And then times 1.5 seconds. If this says 0, that would be a good sign. If it doesn't say 0, we're in a lot of trouble. It is 0. Right. Remember, guys, my calculator is in radians. Right? Your calculator has to be in radians to make this work. Okay, has to be radians. Okay. Is that okay? Okay. All right. Next question then is, what does velocity versus time look like? So let's come up with an equation for that. So velocity versus time. Okay. So I can keep the 0.01 meters here, but I have to also extract this angular frequency, which in this case is like 3.14, and that'd be hertz. Guys, hertz is like 1 over second. So, oh, look, what I have, meters and over seconds, that's meters per second. Okay. And then cosine changes to negative sign. So I also got a negative slack on it. And then this part stays the same, 3.14. So hertz right there. Okay. That should be the equation of my V versus T graph. Okay. So go ahead now. Okay. So here's your X versus T graph. Here's your V versus T graph. Okay. Go ahead and draw that graph, the velocity versus time graph. Go ahead and draw the velocity versus time. Give you guys a minute. I think Alex got figured out. Hector got figured out. Hans got it figured out. Let's got the Alex got it. Alex got it. Evan got it. Sure. Nathan got it. Yeah, these are looking good. They're pretty good. Okay. So, you guys know that the sine graph starts at the origin and then it goes immediately up and makes a hill. So this is negative sign. So it actually starts with a valley. Now, you guys, does it still take 2 seconds to cycle? Yeah, so it takes 2 seconds to cycle. That's gonna look more like there's one full cycle. Okay. And then next 2 seconds, like that, next 2 seconds. Okay. So there you go. There's 3 cycles, which takes 6 seconds. Let's see that. Okay. Now, one reason I'm putting all these graphs together with you guys and taking some good time with this is because I think there's a good chance that they're going to ask the question that I'm about to ask you right now, which is this: is what is the maximum speed of that block? Actually, I have a question leading into that. What location would the maximum speed of the block be? Yeah, that's going straight through the equilibrium point. Yeah, that's true. Right? Even if you turn this horizontal. Okay, all right. So in this case, the equilibrium string would be stretched a little bit, but that's good. Oh, yeah. So what is the maximum speed? What's the maximum speed? Might be a way you can get also through conservation of energy, but we're looking at this particular method. Because wouldn't that be the magnitude of like the amplitude of the velocity versus time graph? Okay. So here, I'll solve for max or actually I see the maximum speed just looking at the equation. Okay. Yes, who can tell me what is the maximum speed of that block? Who knows? Who knows what is the maximum speed of that block? Here's one way to think of this: is I see this graph is sort of constrained, right? It goes up so high and it goes down so low. Right? Based on this part right here, guys, sine of anything maxes out at what? One, right? You can sit there and plug in sine of blah 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 and just punch in numbers all day, and this will never get bigger than 1, and it'll never get less than -1, right? Because that's what sine is. Right? Sine by itself oscillates between -1 and 1. Right? Then, if you take that, so let's say it maxes out at 1, and you further multiply it by this amplitude, then wouldn't this amplitude, in this case, represent the maximum value? In this case, maximum speed. So what's that? 0.0314 meters per second. Okay. So I can say V max right here is 0.0314. That'd be meters per second. Okay. 0.0314 meters per second is your maximum speed. Okay. All right. Last one, acceleration. Let's just do the graph for acceleration. All right. So this would turn into a negative cosine, which is going to look kind of like the x versus t, but upside down. So it takes 2 seconds to cycle, right? You guys can follow the pattern and do that. Something like that. Okay, so there you go. There's acceleration versus time. So you guys good with the oscillation there? Blocks and springs? Okay. All right. Any questions on any of that stuff? Any of that oscillation stuff? Okay. All right, let's get one more look at the poster version, which is, there you go. There's the poster version of everything we just did. Okay. And again, I'm here. I bet there's a good chance you're going to get the question, what is the maximum speed? This is one way to do it, is to go through that whole process we just did and do the regular amplitude, say in meters, times 2 pi times the frequency, right? Would give you the answer to the maximum speed. All right. So let's go into fluids. All right, I got real general states of matter here. States of matter. Okay. So, let's see. How would you define or which two of these represent fluids that AP could ask you about? Maybe liquids and gases are considered to be fluids. Right. That's something that doesn't have a definite shape. Right, guys. Anything that doesn't have a definite shape. So liquids and gases. Okay. Now the difference between a liquid and gas is a liquid has a defined volume. And a gas does not have a defined volume, right? A gas can expand and contract. Liquids, I mean, a little bit, but basically not compressible. Okay. So, AP is not going to ask you this. I just want you guys to do this. Ideal gas law. So there's a relationship between pressure, volume, and temperature. It goes like this. Right? If you change one of these, it changes something else. Right? The AP is not going to ask you that. So let's keep going. Okay. Density. Here's one good to know. So, guys, what Greek letter is this? Rho, yeah, this Greek letter rho. Right. You guys see it's going to be for density, which is a ratio of mass to volume. You guys, this is an intrinsic material property. So once you know the material, for example, if I told you water, did you guys say water is always going to be 1,000 kilogram per cubic meter? Yeah. Now there's little variations, temperature differences in salt water and blah, blah, blah. But basically, it's called 1,000 kilogram per cubic meter for water, and more than that for metals, which are going to sink. Okay, so you have that. All all right, Archimedes principle. This is the one that tells you the value of the buoyant force, or the magnitude of the buoyant force. Okay. Now, guys, which direction does buoyant force always push? Up. Yeah, it pushes you up. Right, try to help you float. Okay. And the reason for that is, do you guys remember the reason why buoyant force always helps you float? Okay. Because as you go deeper and deeper in the water, doesn't the pressure increase? And if objects are three-dimensional, then the bottom of the object is a little more pressure than the top. So there's a net force upward. Okay, so buoyant force equal to it ends up being equivalent to the weight of the fluid displaced. Now you can take that piece of knowledge and turn this into an equation. So the buoyant force, so this upward acting buoyant force is equal to, well, let's see, weight of fluid displaced. Wouldn't that be the mass of the water displaced times gravity field, mg? And the mass of the fluid displaced is its own density times its own volume. So density times volume, which just this rearranged, isn't it? Okay, so let's look at ratios here. Okay. So we're looking at these formulas down here. Okay. Now, when AP gives this to you, get a good look at how AP writes this. Buoyant force is equal to rho VG, which is the same thing I have here, rho VG. Okay. But because AP does not specify which rho, which density, and which V, which volume. Like if they gave you this exact scenario, are we talking about the density of the lab weight material or the density of the water? The density of the water, right? So it's kind of ambiguous on their page, but here it's spelled out. But now you guys know to look for that. Okay. So talking about the density, not of the object itself, but the density of the surrounding fluid. And then volume displaced. So if the entire object is submerged, then it would be the volume of the object, like my picture. But if something's like floating above the surface, yeah, like I think I haven't, like this iceberg coming up. Remember, this iceberg that's floating is not pushing water out of the way equal to its own volume. It's only this volume underneath the water. Okay, so it's part of its volume. Okay, so watch for something like that. All right, so you guys know Archimedes principle. You guys can navigate that. Okay. All right, so here's a nice experiment. So if this object weighs 10 newtons, which is actually this one right here. So if I put this on a spring scale, it says it weighs 10 newtons. Bam. Let's say I put this in water and the weight reading, or the tension of the string, I should say, goes down to 7 newtons. Well, that means that the buoyant force must be equal to 3 newtons. And if you capture that water, say if it's spilled over and weighed it, that's exactly what it would show. All right. So here we got 2 concepts on this page. There's force and there's pressure, right, which are related to each other, but they're different units and they're different concepts. Right? So here's Archimedes' principle, right? The buoyant force is density of the surrounding fluid, in this case water, times the displaced volume, which is not the volume of the entire object necessarily, and then times gravity field. Right? So these Archimedes. Okay. Now pressure is a really similar looking formula. I still got the density of the surrounding fluid, right? I still got a gravity field in the mix, but instead of saying displaced volume, which would lead to a force, right? You just say how deep is it, right? Which leads to a pressure. Right? Hey guys, what is the relationship between the left half of the page and the right half of this page? What's the relationship between force and pressure? Can you guys say force is equal to what? How do you get force from pressure? Pressure times area. Yeah, pressure times area, right? Or you could see it the other way. You could say pressure is force over area, right? I mean, those are the same thing. You see that? So, in fact, that's the difference between, say, a volume and a depth, right? Is it's missing some kind of meter squared to be like an area, right? That's it. All right, so you guys go with force and pressure. All right. Ooh, here's a fun application of this is what percentage of this iceberg is submerged in the water? Suppose you know the density of the ice and you know the density of the water. Because which density is greater, the ice or the water? Yeah, the water's more dense. Yeah, the water's more dense than the ice, so now the ice can float. Right? Okay. Let's say I threw some numbers at you guys, said like what percentage is submerged by that. Okay. So guys, what framework would you use to solve this? If you see a bunch of forces and it's just at rest, what framework is that? Is that force equilibrium? Right, force equilibrium. Right. So if I got any question about that, this would be my first step. If this was an FRQ, that would be the first thing I would write, and I'd probably pick up a point right there. Say, oh, okay, this student clearly knows this is a force equilibrium question. Right? It's not conservation of energy, it's not conservation of momentum. Right? Right. So now what? Well, I see two forces, so the one up minus the one down should zero out. That's probably my next step. Let's see if that's true. Yep, that's exactly the next step. So the point force up, the weight down, zeroes out. Okay. Now maybe I want to substitute in an expression for buoyant force, that'd be your rho VG. Okay. And I could also substitute the mass of the ice with density times volume of the ice, couldn't I? Okay. Here, guys, write it in your paper. See if you guys follow what I just said. So I just told you verbally how I'm going to get the next step, or what I'm pretty sure I know what the next step is. Write the next step. See if you can do that substitution. Right. So we set up a force equilibrium. Say, okay, well, here's my free body diagram, which you probably also draw if this was a free response question. Okay. So I know the force up minus the force down has to zero out, be 0 newtons. Okay. And now we're about to make some substitutions. We're going to substitute in some expressions. Okay. Okay. So did you guys write the next line? Okay. You guys got it? Okay. Let's see what I did next. Okay, so I'm going to substitute that into there. Force buoyant. Wait a minute. What did I just do? Okay. All right. I confused myself. All right. I did things in a different order. Okay, that's actually what I was looking for. Something more like that. Okay. Okay. So here's rho VG is the buoyant force, but it's the density of the water. And notice it's not the entire volume of the ice cube. It's just the displaced volume, which is just the part that's submerged. And then mass of the ice replaced with density ice and volume of the ice. Right. So if you have something like that, that'd be good. Okay. Now, what's the same, what's different? Guys, are these densities different from each other?
Yes.
Yeah, so it's two different materials. Are these volumes different from each other?
Yeah.
Yeah. Right, so this one on the right side is the entire ice cube. This one on the left side is only the submerged part. Are these gravity fields the same?
Yeah.
These gravity fields are the same. So should that cancel out? So if you had a big old pull on, say, the surface of Mars, would the answer be the same? Yeah, because gravity field cancels out. As long as you have gravity, then it doesn't matter how strong it is. Okay. So you'd probably be solving for something like this. Well, great. What is the ratio of this displaced volume compared to the entire volume? Right, guys, yeah. All right, and then you have rearrange the rest of the equation. Yeah, gravity flow cancels out. It ends up being that. It's the answer to that particular question. Okay, so there's a good classic physics question. You see something like that. That's how you think about that, how you approach that. All right, so you guys good there? All right, next one I have lined up is Pascal's principle. Guys, what does Pascal's principle say? Yeah, something to do with pressures, right? Force over area, something to do with pressure. Do you guys know pressure in a container is transmitted undiminished? Actually, I think I remade this page. I got rid of the sign. It says equal pressures at equal depths. That's only true if it's the same fluid and if it's not flowing, right? That you could say something like that. Like this hydraulic lift. That's what I have here, hydraulic lift. Now, you guys see this hydraulic fluid here? Isn't the pressure the same everywhere? I mean, maybe at different depths, it's slightly different, but that aside, it's basically the same on the left side and the right side. Okay? And that should be exactly true if you look at the exact same elevation. So pressure is the same left and right, which is force over area equals force over area. Now I have two different external forces, right? Maybe this input force on the left side and the weight of this car on the right side. Ooh. Okay? And two different cross-sectional areas on those pistons. The ratio of force over area stays the same. So if you have a small force on a small area, that could lift a large force on a large area, right? Because it gives you the same ratio. Is it? Now the catch, because there's always a catch with these, you're getting a mechanical advantage, right? You can lift something very heavy with a small input force. Okay? I remember with the pulley system, the catch is you have to pull lots and lots of string. The sort of equivalent here is how much fluid actually moves. Now it's the same volume change. Right? So the volume that leaves the left side, the volume of hydraulic fluid has to increase on the right side. Okay, but the height change is not going to be as much. So you can push down like a meter on the left side, and maybe it only raises a couple of centimeters on the right side. So that, right? You guys, right. So you guys go with that hydraulic lift right there, right? And all this setup. Okay. Right. Now this next one, guys, you're going to get a question about this. You're going to see something like this on the AP exam. This is just such a classic question. Although they've never asked this before, but they've never had fluids. Well, at least for the past about 10 years. Here we go. So I got this YouTube got different fluids in it. It looks like I have 4 different liquids, and there's also the atmosphere pushing above. Don't forget that also, because there's also variations on that. Like you can close one side and that changes this a little bit. Okay? But my setup here is I can pick some elevation where there's definitely the same pressure. Like I definitely see at this bottom line here, would it definitely have to be the same pressure, left side and right side? Okay? And actually that's true going up into these arms, the left arm and the right arm, right? Same, right? Right until you get to this point. Right. Now, even at this point, guys, are the pressure still the same right at this point, left and right? Yeah. And that's where that stops being true, everything above this line, because now I have different fluids. Right? Maybe there's some kind of oil here and a different kind of oil here and a different kind of, so different. Right. So I can go through, I know pressure is rho GH. Right? You guys called that a few slides ago. Pressure is rho GH. So if I get to this bottom line, if I do all the rho GH is added on the left side and all the rho GH is added on the right side, it all has to equate. Okay, isn't that true? Do you get the same pressure? So let's do some accounting. Now I have the pressure from the atmosphere. That's this one here. I got this rho GH naught from this blue. I got this rho GH1 from also this blue. Right, so it's the same liquid here, just broke it down to different heights. Okay? I got this rho GH from this gray liquid. Okay, so add all that up, adds up to some pressure here, some number of pascals. Maybe it's like, oh, I don't know, 150,000 pascals or something. Okay. Okay. And then on the right side, well, it has to be the same pressure, but we got there from, there's a different journey to get there. So how's that go? Oh, so I still got the same atmosphere over here. Notice atmosphere. So both ends are open to the atmosphere, just in this example. Again, there could be a variation on that, but that's not true. But and then I got this rho GH knob here. I got this rho GH from the green. I got this rho GH from the gold, and I add all that up. Okay. Now left and right, since it's both open to the atmosphere, left and right, and that's just going to cancel. This rho GH naught is the same left and right, so that cancel. Okay, and here's what's left over. Okay, so if you were, well, you guys know how these things work. There's some number of variables here. They might have you solve for something. Like if they gave you all the densities, they might say, like, how deep does this have to be to balance this equation? And then you solve for H4. Or if they give you all the heights and maybe you don't know what material, what kind of material is this? You could solve for this density, rho 4. Okay, you guys can do that? Now that I'm looking at it, it looks like the gravity field would also cancel everywhere. Okay. Okay. So you guys could solve the YouTube. Solve YouTube. Okay. All right. Ready for the next one? Okay. So far, there's all the fluids examples we've been looking at have all been stagnant fluids. There's nothing been in motion yet. But these next few are going to be in motion. So these two go hand in hand, conservation of flow and Bernoulli principle. In fact, if you're getting a Bernoulli principle question, there's a good chance you'll have to solve conservation of flow first, and then you can go to Bernoulli. So these really go hand in hand. Okay. So conservation of flow. I can say that the flow rate is the same everywhere in a pipe system. Now I got different pipes. I got a thick pipe here, I got a thin pipe here. Okay. But the number of gallons per minute is the same everywhere, or cubic meters per second. So that's quantity per time. Okay. Quantity per time. Okay. Flow rate. Okay. And here, let's actually derive that. I think I designed a new poster in the past couple of weeks that was something like this. Okay. So I'm looking at quantity, or let's do volume over time. So volume over time. So volume 1 over time equals volume 2 over the same time interval. Okay. Okay. So if you're watching, say, like if you plot a gallon here per second, it'd be like 1 gallon per second over here. That'll look a little different. Okay. Okay. So, guys, what is volume in terms of this cross-sectional area? Would it be this area? Time here, just redraw this. Would it be like some cylinder? Like I could make some cylinder right here. Could be some volume of liquid, and then downstream over here, you could have some other cylinder roped off with something like that. Okay, guys, could let's switch to peaking. Okay, good. This volume right here that I just attached in equal this volume right here I just attached in. This could be the same volume. Okay, and they both take 1 second to move, something like that. Okay. It's the same flow rate. Okay. Okay. But you can already see which one's moving faster. Because which is moving faster, the one on the left or the one on the right? Yeah, the one on the right has the faster linear speed, doesn't it? Faster linear speed. Right? That's what we're about to get out of this. So if I know this cross-sectional area, in this cross-sectional area, it's called A1 and A2, and I know this distance here, call this X1, and this distance here, call this x2. Wouldn't the volume be cross-sectional area times that width vector? So that's my next substitution. Instead of volume, I'll call it a1 x1. And that's divided by t equals, and I have a2 x2 over t. Okay, so like that. Right, now I can rope together these variables differently. If I went backwards and say, oh, area times x, that's volume, at least back to where I started. But if I rope it together this way, guys, what is x over t? What is that? Velocity. And you guys see that that is this gold box right here, this gold box right here. Right. Yeah. As long as the fluid is incompressible, and you guys can assume it's basically true. Yeah. A times v equals a times v everywhere. Okay. Now, do you guys see this green box right above it? This is more complicated. You might see this in college, maybe. Right? If there could be a density change, or if you're pushing air through and the density would change, you also could include the density to make the flow rate work out. But you guys don't worry about that one. So I'm just going to cover that one up. All you guys care about is this gold box right here for water. Okay, so go do that. All right. Right, so after you solve that, and you again, you guys know the speed's changing. You guys told me that. You guys told me V2 is greater than V1. Then you can consider what's going on with pressure. Because what happens to pressure when a fluid speeds up? Does the pressure increase or decrease? Decrease. Yeah, it's a decreased pressure. Yeah, let's do the experiment again. So if I have a piece of paper and I blow a stream of air over the top, I have a fast moving fluid, air. It should vacuum the paper up, shouldn't it? Let's see if this still works. It does. You guys see every time I blow a stream of air, it vacuums it up. That's this one right here. Right? So I think I derived this with you guys from conservation of energy. Doesn't this look a lot like conservation of energy? Some energy plus mgh plus 1/2 mv squared equals blah, blah, blah. Energy is conserved. Right? But in terms of fluids, you place mass with density and you get a valid formula that's in pressure units. Looks like that, pressure units. So let's solve something like this. Okay. Let's say got a pipe system. I'll make it look just like the poster. How about that? I'll throw some numbers at you guys. Let's say that this radius, because AP would probably give you radius, is 0.25 meters. And let's say this radius, called R2, so R1 and R2, is like 0.10 meters. Okay. And let's say the original velocity, I'll call this V1 equals 10 meters per second. Okay. So solve for V2, which is going to be faster, of course. Okay. And I also want to know something about pressure. So I have to tell you the height change here. First one about pressure. Okay. Let's say this height change is about 1.5 meters. Okay. Let's say the initial pressure, I'll call this P naught. P naught equals, let's have that be 170,000 pascals. All right, those are fairly reasonable numbers. Okay. So I want to know the pressure in the top pipe, like if you're a fish swimming around, what pressure you feel, but you can't solve that until you solve conservation of flow first. Right. Okay, we got about 3 minutes, so I have to solve this with you guys. Okay, can you guys go along with me? Okay, right. Otherwise, I would have you guys solve it first. So let's do conservation of flow. So, all right, conservation of flow is going to be step 1. I do A1 V1 equals A2 V2. Okay, now here's where we got to break out some geometry. Guys, what is the area based on radius? Pi r squared. So pi r squared V1 equals pi r2 squared V2. Okay, and now I know all those numbers except for the V2. In fact, the pi just cancels out. This makes it a circle, whatever. Okay, do the fast version of this. So I'll plug in 0.25 meters here. I got to square that. Right, got to square the radius, make it like an area. Multiply by this initial velocity, which is 10 meters per second, and then divide by, and the radius 2 squared, so it's 0.1 meters being squared. I'm getting V2 equals 62.5 meters per second. Does that look about reasonable? It looks like it's sped up by a factor of 6. That looks about right, right? Okay. Okay. All right, now let's flip over to Bernoulli. You guys ready for Bernoulli? Okay. So it's Bernoulli time. Bernoulli. Let's go initial pressure plus rho g h naught plus 1/2 rho v naught squared equals pressure final plus rho G H final plus 1/2 rho V final squared. Great. Now, we're solving for this other pressure. That's the question. Rho GH count, let's call it 0 because initial height could be 0. Okay? And everything else we plug in. So I told you guys 170,000 pascals. Here, got 1/2. Oh, guys, what's the density of water? Yeah, 1,000 kilogram per cubic meter. You guys can use that. And it was going at 10 meters per second. Where that? Okay, we're solving for this pressure final. Plus, okay, rho GH. So I got 1,000 kilogram per cubic meter. Let's call it G 10 meters per second squared. And it was going a height change of 1.5 meters. So that's sorry, something like that. Okay. And then plus I got this 1/2 rho V squared, 1/2 1,000 kilogram per cubic meter. And the final velocity was 62.5 meters per second. We got that from conservation of flow. That's why I had to solve first, and that's being squared. All right, so let's see if I can beat the bell here. I don't know if I'm going to, but yeah. Try this anyway. If time runs over, I'll just put this on the video. Good day. I'm just gonna finish this calculation and post the recording. All right. Did I do that right? 1/2 V squared.
You only bring it back where.
Yeah, you can do it. Okay. Okay, well, okay. Check that tomorrow. All right. It is. Oh, yeah.